Okay. So basically now in today's live lecture, we will go through some of the things that we have covered in the course and try to get a summary of what we have learned in the course so far. So I will just go through quickly through all the slides or all the lecture sessions that we have covered, briefly underlying the philosophies behind what we are doing. So at first we said that we started with a basic understanding of converters, in which we said that when we have a source and a load, then we basically want to control the flow of power from the source into the load. Of course, we can do this with the help of a resistance, but resistance is a lossy element. So we use a switch instead of a resistance. And then when we use a switch, it is possible to have a very efficient flow of power or flow of energy from the source into the load, from which we get the concept of pulse width modulation, okay, PWM. And when we do the PWM, we have to remember that the load can be actually, in a power electronic circuit, it can be kind of like a current source. It may not be always passive load. So therefore, if we want to feed energy from a voltage source into a current source or vice versa, then this switch has to be properly designed. Why? Because current source cannot be opened, like voltage source cannot be shorted. Okay, because they are dual in nature. So therefore, we have to make some arrangement of switches. And one of the arrangement that we very frequently do is like this complementary switch actions. Okay, S1 and S2 are complementary. And one of the practical realizations is this kind of like a IGBT diode pair or a MOSFET diode pair, okay, for the voltage and current sources. And then we find that what is the rating of those switches, what is the voltage rating, current rating. This can be understood by seeing the blocking voltage that the device has to withstand or block. And we have to see the current that is flowing through the devices. Okay. So we can find out the ratings of both IGBT and diodes. And once we understood that there is this switch arrangement is something like this, then we find that these actually are very similar to what we have already studied. Many of you have already studied in your undergraduate courses. These are called the buck converters and boost converters. But of course, we do not realize these switch arrangements when we study buck and boost converters, but it actually comes from this basic principle of energy exchange between a voltage source and a current source. Okay, so this was something which led us to one of the basic building blocks of what we are going to study in this course. We have already studied, that is the half bridge converter. Okay, in half bridge, you have these two switches, S1 and S2, which are controlled switches. And also we have the two uncontrolled switches, D1 and D2. Okay, so we can find out what are the uh, what are the ways by which this S1, S2, D1, D2 will be turning on and off like that. Okay, which device will conduct under what circumstance? These things can be understood from the circuit diagram. Positive voltage, negative current, negative voltage, positive current, and all those divisions. So this was the basic understanding of the half bridge converter. And with the half bridge, now it is possible to have a full bridge converter by adding one more leg. So in this case, what is possible is that now we have 8 switches, I mean 4 switches and 4 diodes, and it will allow a bidirectional voltage across the load and a bidirectional current through the load. So the current can flow from left to right or right to left in the VAB voltage that is coming across this RL load in the circuit. So this is what is also explained in these. And then we say that, of course, we can turn on and off the switches using pulse width modulation, where we can change the duty ratio of each switch by comparing this modulating wave with a high frequency triangular wave. If you move this modulating wave up or down with respect to the high frequency triangle, then you can change the duty ratio of the switches. And that means the width of the pulse being applied to the switches. Okay, we usually keep the triangular wave height to be 1, but the modulating wave height will be M. And so the average voltage which comes across the load, that can be changed by changing the position of the modulating wave with respect to the triangular wave. So the average voltage VAO is in fact is equal to VAO average is equal to M times VT, where VT is the DC bus voltage magnitude and M is the height of the modulating wave, where 0 less than M less than 1. So now we also say that actually M is not a fixed value. M can vary from cycle to cycle. Whatever we had said earlier was where the M was in one cycle. So when you have M varying from cycle to cycle, then you go into something called as sinusoidal pulse width modulation. One possible implementation. You can have other types of modulation. Okay, you can have a non-sinusoidal modulation, you can have a trapezoidal modulation and anything. But if you have a sinusoidal modulation, then the output voltage of the converter will be varying sinusoidally with time. Okay. So this is basically what we know. This is basically what is understood as the converter operating with sinusoidal pulse width modulation, where the output voltage of the converter is controllable. So the converter becomes a controllable voltage source with the value of M equal to 0 or M equal to 1. You can change the output voltage magnitude. Okay, between if you put M equal to say 0.5 or 0.3 or 0.4, then the output fundamental RMS voltage will be changing the magnitude. The magnitude will be changing. Okay. We do not usually go into over modulation, although it is possible to go, but we generally avoid that because it generates lower order harmonics, 5th, 7th, etc. Okay. The most extreme form of this modulation is the square wave operation, where you actually turn on the switches for 50% of the duty, 50% of the cycle. This is the maximum voltage that you can get out of the converter. And if you do a Fourier analysis of this square wave, you get that the output fundamental voltage is 4 by pi times into Vd by 2, which is about 1.27 times that which was obtained with sine PWM. So with square wave operation, you get about 27% more than 27% more fundamental voltage as compared to what you can get with sine PWM. Okay, but this comes at a cost. You will generate lower order harmonics, 5th, 7th, etc. So square wave is possible. Again, it is avoided, but if it is necessary to do, then you may go into the square wave. We had some time back doing some work in a project where we had to do actually the square wave operation because the DC bus was very limited. So we were not having enough DC bus voltage magnitude because of some other constraints. So there we were running a motor, and in that motor, actually we had to we had to adopt the square wave operation, knowing fully that we will be generating lower order harmonics, but that 27% whatever was extra possible with sine PWM, that is something which was necessary so that we can produce sufficient voltage for the motor. Okay. So this is the full bridge, and yeah, these are some of the waveforms. Again, half bridge can be extended to three-phase circuits because three-phase is nothing but a combination of three half bridges. Okay, and therefore the modulating waves will be phase shifted by 120 degree, and then you will see that there will be a common mode voltage between this point N and point O. Okay, this common mode voltage will always exist between N and O. So therefore, you cannot connect actually the points N and O. Then if you connect it, then a huge current will flow between the points N and O. Okay, so this has to be avoided. Okay, so this common mode can be extended for getting the space vector also when we do the space vector PWM. And so these are some of the load voltage magnitude expressions. These you can find it out yourself. And you can see the difference between half bridge, full bridge, and three phase, how much voltage is possible from the converter. Okay. Now, yeah, so this, what about the harmonics? In harmonics with sinusoidal PWM, we see that there exists the harmonics at around this MF frequency, where MF is the ratio of the carrier frequency to the fundamental frequency. Okay, here you can see, if you do the harmonic spectrum, if you see this harmonic spectrum of the voltages, suppose I am showing the pole voltage, there you can see that I have taken 21, MF equal to 21, and the harmonics exist at 21, 23, 25, and also 19, 17, etc. Okay, but the magnitude of the harmonics is not very important. What is important is the position of the harmonics. Okay, of course you will say that why the magnitude is not important and what will happen. Generally, nowadays the devices are so powerful that we easily can switch power devices at 10 kilohertz or more. And if you compare that 10 kilohertz with respect to 50 hertz, then you will see that the magnitude, the harmonic MF will be around 200. Okay, so 200 times you are away from the fundamental. So the magnitude of the harmonics there is not so important, because anyway we will filter it out. Suppose we will put a filter at the output of the converter, and we will get rid of these harmonics. But the corner frequency of the filter is dependent on the position of the harmonic. Okay, so if the harmonic is far away from the fundamental, then we can also place the corner frequency of the filter far away from the fundamental. If the corner frequency is high on the far away from the harmonic, from the fundamental, then the size of the filter also reduces. This we have explained in the slides, in the lectures. Okay, so again, there are certain conditions for the harmonics like odd multiple of 3, etc. Okay, so this was one of the basic understanding of the converter. Now, next we will just hold on. Okay. Next, we will have the third harmonic one. Okay. So then we have this third harmonic addition with sine PWM. Okay. In this, we said that we can actually add a third harmonic with the fundamental voltage. And when we add the third harmonic, this because the load is star connected, the third harmonic voltage. So we can think of the third harmonic as something like one controllable voltage source on A phase, as well as B phase, as well as C phase, one controllable voltage source, which is having, I mean, if there is any equivalent circuit, okay, the equivalent circuit is not shown here, but basically it shows that there is a controllable voltage source, and that controllable voltage source is producing a fundamental as well as a third harmonic. The third harmonic voltage exists in the pole voltage, because you can think of that switch getting replaced by one controllable voltage source, which is generating a third harmonic. Now, this third harmonic will not be able to force any current through the load, okay, because the load is isolated. The load, the neutral point is isolated. It is not connected anywhere. And in this isolated neutral point, the sum of the three currents is always zero. So therefore, the third harmonic voltage, if you generate by switching action through the switches, it will exist in the pole voltage, but it will not be able to inject in any third harmonic current into the load. And this is what we take advantage of. We say that we will inject a third harmonic in such a way that we can extract more fundamental out of the DC bus of this converter. Okay, and this can be understood by the waveform which is shown here. The original black colored sine wave is the one which has a modulation index of 1. Then we add a third harmonic of a certain magnitude. In fact, it is 1/6 of this fundamental, and in phase with this black colored big sine wave. When we add these two, we find that the resultant waveform, which is the red colored waveform, that waveform is actually going down in magnitude. Its amplitude is lesser than the black colored waveform, immediately indicating that there is now an extra margin where we can actually increase the black colored waveform amplitude by this extra margin. Okay, and this extra margin is about 15%, which is in fact shown by the mathematics here. And with this extra addition of the third harmonic, which is 1/6 of the fundamental, we can get about 15% more DC bus utilization. Okay, because the fundamental can increase by 15% more. So these are shown by these examples, where you can see on the top diagram the m equal to 1 and m equal to 1.15. That on the lower diagram, okay, at m equal to 1.15, the fundamental has actually crossed 1, but the resultant waveform is just able to touch the 1 and -1 lines. So this is what, when we do the harmonic analysis, then we see that the third harmonic is present in the pole voltage, but it will be absent in the line voltage, and it will also be absent in the load phase voltages. Okay, so this is the advantage of the third harmonic. Then we go into what is called as space vector PWM. So space vector PWM comes from the space vectors, which is a concept, it's a mathematical concept, and it's very useful for visualizing the effect of the three-phase variables in space. Okay, now in this case, we see that we can define the space vectors in such a way, VRT, this is the definition of space vector, which is valid both for balanced as well as unbalanced case. So this is a visualization of space vectors when you have a balanced set of phasors. Okay, then you can see how the space vector, current space vector, is rotating in space. So the space vector can be applied to any variable. So you can have a space vector of the pole voltage, load phase voltage, load current, etc. So now we find that space vector is related to the converter switching states, because when you put different switching states, of course, there are 8 switching states possible from the converter if it is a 3-phase 2-level converter. Then if you have 8 switching states, 2 to the power 3, then you will, by using these 8 switching states, we can have actually different 6, we will have a space vectors in which there will be 6 active vectors and 2 zero vectors. Okay, so you can find out how these space vectors will be, how much is its magnitude as well as its angle when we apply these 8 switching states, which are given by, for one combination, say take a combination of 1 0 0, and then we can find out the load phase voltage space vector VAN by seeing VANT, VBNT, and VCNT. Okay, and then we see that the VRT, that the resultant space vector is 2/3 VD e to the power J0, means at an angle of 0 degree. Remember, space vectors are functions of time. Okay, so this is the instantaneous space vector. Okay, it's a function of time, and the space vector may or may not have equal radius. In case of an unbalanced system, the radius of the space vector, instant by instant, it is changing. It may be elliptical in shape. It may be existing in three-dimensional also. Okay, so for different combinations of switching states, we can have different space vectors, VRTs, which we will categorize into 2 parts, zero vector and active vectors. And these are actually represented diagrammatically on a diagram, okay, which is known as the space vector diagram. In this space vector diagram, there are 8 vectors which are marked by these red colored dots, okay, which are the endpoints of these vectors, as well as the 2 zero vectors. Okay, so for convenience, we actually put a boundary on this space vector diagram, although this boundary does not exist. It's an imaginary thing, but for our convenience, we put a boundary around it. And then we, with this boundary and with these space vectors on the 6 sides, okay, we can draw the space vector diagram, and we divide the whole space vector diagram into several sectors, 6 sectors in fact. Okay, so then when we do the space vector PWM, how do we do it? Okay, we use these space vectors from these 6, from the sides of the hexagon as well as the 0 vectors at the center. So suppose we have to realize this VR, the reference vector. So we are trying to produce one space vector VR, and this space vector can be realized by switching V1 for certain duration, V2 for certain duration, and V0 for a certain duration. Okay, by using these 3 vectors, we will be realizing the reference vector VR. Okay, so the relationship is something like this, which is shown: VR into TS equal to V1 T1 plus V2 T2 plus V0 T0, where TS equal to T1 plus T2 plus T0. Now, in space vector PWM, T01 is equal to T07 is equal to T0 by 2. And then you can find out all the mathematics behind it. Basically, the space vector, in space vector, we make the 2 zero vectors equal at the beginning and at the end of the cycle. Okay, so you can have one set of switching, like you can go from switching 0 0 0 to 1 0 0, 1 1 0 and 1 1 1, or you can go from 1 1 1 to 1 1 0 0 1 0 and 0 0 0, something like this. Always you jump from one vector to the other vector, remembering that always one switching state actually changes, okay, out of the three. Now, when you do this thing, you find something very interesting happening. And this, okay, first we find that the maximum voltage which is possible in space vector is denoted by the circle which just fits, or an inscribed circle which just fits inside the hexagon. And the length or the radius of this circle is 0.577 VD. Whereas in sine PWM, the length of or the radius of the circle is 0.5 VD. So in space vector PWM, we get 15% more DC bus utilization as compared to sine PWM. Okay. Now, space vector PWM can be also realized using carriers. And this involves like observing the carrier-based sine PWM technique in a little bit more details. If we observe it carefully, the pattern of switching, what happens in sine PWM, we find something very interesting. What is it? We find that the same pattern of the switching of 111, 110, 100, 000, the same pattern of switching also happens in sine PWM. But there is one difference that is there with the sine PWM and space vector PWM. That difference is that the two zero vectors at the beginning of the cycle and at the end of the cycle, these two zero vectors are not equal. That is what happens in sine PWM. Whereas in space vector PWM, the same pattern of switching happens. However, in addition, the two zero vectors at the beginning and at the end, they are all of equal time duration. Okay, so we say that the difference between sine PWM and space vector PWM is that the two zero periods are unequal in sine PWM and they're equal in space vector PWM. Once we do that, then we see that these three carriers basically become centered around the carrier, which is spanning between -1 and +1. It comes at the center, and there is a slight modification that happens for this centering, which is done by this common mode addition. Okay, so if you add this common mode voltage to the original sine PWM signals, you can make the two zero vectors equal at the beginning and at the end of the cycle. And this VCM is given by minus of Vmax plus Vmin divided by 2. Okay. So this is the advantage of the common mode, which can give you. So this is just a one line of code actually in a DSP implementation. It's just a single line of code which you will add, and then you will change from sine PWM to space vector PWM. Okay. And so you can see the resultant waveforms which we get here. Okay. Now we will see another slide which was part of week 3. The week 3 is this. Okay. So we briefly touched upon the different types of power switches, which I plan to have in more details in the gate drivers and all. But generally, we use for this medium voltage nowadays, all are IGBTs or MOSFETs. And silicon carbide is also kind of like catching up. Okay, and we expect that in near future, silicon carbide is going to be the most dominant player in this market. Okay, thyristors are still used, but again at very specific applications. Okay. So there are several manufacturers, and you can see some of these manufacturers and see how the data sheet and all this. Now, Then we started with the multi-level converter, and we started with the cascaded edge bridge converter. In cascaded edge bridge, we have this is the basic idea of multi-level, where you get many levels in the output voltage so that you can get a voltage waveform which is very close to a sine wave. It has several advantages, like you can use lower rating devices, your filter requirement goes down, and etc. Many more. Okay, so one of the important topologies of this multi-level converter is the cascaded edge bridge converter, okay, which has many cells and they are connected in cells which is like edge bridge, and they are connected in series with each other. Each edge bridge produces 3 levels of voltage: 0, plus VDC, and minus VDC. And then when you cascade them, you can get more and more number of levels. And with n cells, you get like 2n plus 1 number of levels. So this is kind of like a 3-phase CHB with 3 cells in each arm. Okay. So actually, it is made from isolated multipulse transformer. This transformer arrangement we have dealt sometime later as part of the multipulse transformer lectures. So different voltage levels in CHB, you can see the VN voltage is 2 VDC or minus 2 VDC. See, the different combinations are shown in the table. Okay, these tables here. And how the switch current flows, voltage, how it comes, all these have been shown in these slides. And how the waveforms get added up one by one. So here you can see that using low voltage sources, a high voltage can be produced at the output of the converter. Now, then we have this slide shows how for if you increase the number of levels, then how the DC sources, that their magnitude goes down and the voltage rating of devices also goes down. Of course, you can argue that we are now increasing the number of devices. If you have a 2-level converter, you have 6 devices. When you have a more than 2 level, accordingly, the number of devices also increases. But then there are also applications where a high voltage needs to be produced, and those high voltages with the present generation of, say, IGBTs or GTOs or IGCTs, we do not have that much blocking voltage capacity from those devices. So we have to, in any case, use series connection of devices. Instead of series connection, we can use this kind of multi-level converters to get higher magnitude of voltages. Asymmetry is also possible, but asymmetrical multi-level converters generally are not very much recommended because you lose the modularity. You cannot, so you can have to have different sets of devices to have this thing. Okay, so this was one of the things that we covered. And then we have the week 4. Yeah. So how do you switch the cascaded edge bridge? We can have both phase shifted and level shifted PWM. Both are possible. So you can both give very similar performance, but there are slight differences. And we have given an example how the phase shift PWM can be used for cascaded edge bridge. So we have total number of levels 11. Suppose you to take 5-cell CHB, then total number of cells levels is 11. Number of carriers required is 10, and the phase shift between the carriers is 36 degrees. And these are shown by this example where you can see the table here, for CHB1, CHB2, CHB3, 4, and 5, how the carriers are arranged. Okay. And the harmonics will be at, say, 400 times the fundamental, that is at 20 kilohertz, if the each is switching at like 4 kilohertz or 2 kilohertz. Each device is switched at 2 kilohertz. So then these are some of the waveforms of phase shifted PWM. And then you can see the resultant waveform. You can see here in phase shift PWM, each module is producing almost identical waveforms. Okay, but they are slightly phase shifted with each other. And that slight phase shift causes the output voltage to be like a more close to a sine wave, which you can see from the blue diagram and the resultant diagram, which is the pink waveform. Okay. So the harmonic spectrum you can see here, it's around 80 times the fundamental, because it is the harmonics, 80 times the fundamental, and it is going to 220 kilohertz when you have 4 cells in the, or 4 or 5 cells in the converter. The same thing can also be done with level shift PWM. Okay, but here there are a number of levels in the PWM waveform in the carrier. Okay, so you have this carrier 1, 2, 3, 4. They are vertically shifted from one another. And then when you do this comparison of sine and the carrier with this logic, which is shown on the slide, then you can get actually the waveforms, which is like this, which is shown here. Okay, it's cell 1, cell 2, cell 3, cell 4. You can readily infer that these waveforms are non-identical for all the 5 cells. Okay, the cells are switching differently. So, but the overall output voltage waveform from the converter is more or less very similar to phase shifted PWM. But here, since the waveforms are non-identical for all the cells, therefore the losses in this level shift PWM is not same in all the cells. The losses, because their patterns are different. Okay. So it is also possible. So you have to rotate the switching pattern if you want to equalize the losses. It is also possible to have a single carrier implementation where you can bring all the modulating waveforms by modifying it and putting it inside one carrier. Okay, bringing it inside one carrier. That is possible. Okay. So these are some of the harmonic measurement, etc. Okay. Now, fault tolerant operation of CHB converter is also something we have covered, in which what we have done is that we say that it is possible to bypass one of the cells and still continue the operation of the converter, but maybe at a reduced power rating. Okay, for which we have a bypass switch, probably with an electronic and a mechanical arrangement. And then suppose we can convert this 555, suppose there are 5 cells, it is operating healthy. Okay, then we denote it by 555. And then when it is faulty, suppose there are there is one faulty cell in B phase and 2 faulty cells in C phase, then we say it is 543. And so this phase voltages become unbalanced during that point. But the line voltages can be made balanced by shifting the neutral of the converter. Okay. Of course, the balanced line voltages have lesser magnitude as compared to the original case. However, where continuity of service is essential, we can still continue to operate the converter at a reduced power rating, but we can still continue to operate the motor. So it's a very fail-safe operation. That is where this kind of arrangement is very useful. And then there is some mathematics involved, how many cells you can bypass and what is the pole voltage. So these are some of the conditions which we have covered in the course. Okay, so this is something which we have also done. Next, we had the MMC, okay, which was one of the very important topics of this modular multi-level converter. Here we say that, so MMC, in MMC, basically, we have the many cells connected in series, and each cell in the most basic version is made up of a half bridge. Okay, and then you have the arm inductors, one DC side, one AC side. Okay, so one of the drawbacks of this cascaded edge bridge converter was that it requires many isolated sources. But in MMC, this DC bus is made up of capacitors. Okay, so, and in HVDC application, hundreds of cells can be connected in series. Okay, so here you can see that these half bridge cells are present, and also full bridge version is also possible. Each cell has bypass mechanism, and the cells are made up of capacitors and switches. Okay. So what are the features of MMC? Very modular, identical cells, low voltage IGBTs, fault tolerant operation, etc. So these are some of the advantages of MMC. And how do you analyze it? You can analyze the MMC by assuming that this upper arm, which is consisting of several cells in series, and the lower arm, they are actually can be thought of as a controllable voltage source. Okay, and once you have this controllable voltage source, you can write down the KCL and KVL equations. And then you can find out what is the magnitude of the voltage required in the upper arm and lower arm, so that energy balance between the AC side and the DC side can be achieved. So here one example is shown where the lower arm voltage can be written by writing the KVL equation. And then you can find out what are the upper arm and lower arm voltage, and you can also depict it pictorially, where you can see here that how the red arrows and the green arrows are shown, where the red arrows corresponds to the upper arm voltage, the green arrows corresponding to the lower arm voltage at several instants of time that has been shown. Okay. So if the DC bus voltage is less than the peak of the AC voltage, then also the operation can be done. But then we will need bidirectional voltage. Okay, so this is achieved by using full bridge cells instead of half bridge. And then we have the rating of the switches, which you can see, voltage rating of switch, and like that here. Okay, so yeah, so the arm currents, which has both a DC and AC component, because some part of the arm current, the AC half of the load current goes through each arm, and a DC component flows through the arm because it has to maintain the energy balance between the DC side and the AC side. Okay, so this expression, so you can see here the IU upper arm current is half of I load current plus I circulating current, and the I load is equal to Im sin omega t minus phi. So the basic energy arm energy balancing at steady state points to an equation where you can see that I circulating, or the DC component of the circulating current, is 1/4 Im cos phi. Okay, this comes from the energy balance. Okay, and yeah, so this will come here, and then the relation between AC and DC side current. Here you can see that ID, the DC side current, is 3/4 Im cos phi. Okay, ideally ID is pure DC. Of course, it is not practical. It has very small ripple, but it is very close to actually DC. Okay, and when you do the arm energy balancing at steady state, you find something very interesting, and that is by doing all this mathematics, you will find that there is a fundamental component, and in the energy expression, the fundamental component in the lower arm and upper arm, they are equal. Okay, but their sum cancels each other. That means energy exchange takes place at fundamental frequency between upper and lower arms. It will not go outside the arms. So that is one thing that you will see in this expression. And also there is a second harmonic term. And the second harmonic term indicates that the energy is getting exchanged among the three phases inside the converter. Okay, because if you add the second harmonic components, then the sum again comes out to be 0. That means inside the converter, a second harmonic flows, but it never goes to the AC side, neither it goes to the DC side. Okay, so this is something very peculiar for MMC. And the MMC bypass operation is also there with the triac and a high bypass switch. And these are some of the simulation results which we have shown. I think we have we do not have much time. So is this Sandeep ji, is it time now? It's almost 1 hour, right?
Yes, sir.
So what should we do?
So you can wind up in 5 minutes, sir.
Acha. So, okay. Another 5 minutes, because I have covered week 4. So I'm just we are trying to summarize. Okay. Another 5. So week 6. So I think we have covered up to week 8 till now, right? So week 6, okay. So let me just quickly go through it and I will cover all the weeks that we have done so far in the course. So yeah, so when you, so with this modular multi-level converter MMC, you can find out this energy balancing, which we have already seen in the previous slide. And yeah, there are several possibilities, and this is something which is very interesting from research point of view. How can you actually think of more possibilities out of MMC? Okay, AC to DC, DC to AC, okay, double star chopper cell and all. Okay, you can have AC to AC conversion, okay, 3-phase to single phase, of course, non-isolated. This is also possible. Then 3-phase to 3-phase, okay, this is the modular multi-level matrix converter. Okay, so this kind of circuit operations are possible once you realize how to play around with these controllable voltage sources. Okay, star connection, delta connection, and this is the hex verter. Okay, like this. So what is the PWM technique for MMC? The PWM, you can use both level shift PWM as well as phase shift PWM. Okay, where you can give this VU star and VL star as the upper and lower reference voltages, and then you can switch the different switches inside. Okay, so these are some of the results which we have shown with level shift PWM as well as phase shift PWM. Another important point with MMC is the sorting algorithm. The sorting algorithm is kind of a bubble sort algorithm that will ensure that the DC bus voltage of all the capacitors are balanced with time. Okay, so here this is basically the capacitor which gets discharged more actually is taken out of the circuit, and the capacitor which is charged comparatively more is inserted into the circuit depending on the direction of the current. If we know beforehand that the direction of the current is going to discharge the capacitors, then we will put that capacitor which is having more charge, and we will take out the capacitor which will have less charge. So in this way, by sometimes inserting the capacitors and sometimes taking them out, we can actually make sure that all the capacitors are having the same value of voltage over a certain period of time. Okay, so this was taken as an example. We had shown an example by which it was possible to do so. Okay, and then we started with the week 7, and in week 7 we talked about the fault and the protection. Okay, where we said that the half bridge has some problems because in a half bridge, when there is a DC pole to pole fault, then the diodes, being an uncontrolled device, they will continue to conduct. Okay, and so it all depends on the AC circuit breaker to open. But in case of full bridge circuits, it is possible to actually limit the current, because in full bridge, the current will pass through the DC link capacitor. Once the DC link capacitor gets charged up to the peak of the AC voltage, the circuit will stop conducting on its own. So therefore, although full bridge has 4 switches instead of 2 switches in a half bridge, people prefer the full bridge sometimes because it has this inherent fault limiting feature in its own. Okay, and this we have shown in the with the analysis that during fault, even the full bridge can act as a back EMF in the circuit, thereby reducing the short circuit current drastically down. And these are some of the pictures from a converter which we have taken from Siemens. They have kindly given us the permission to reproduce it here. And we see that this is an offshore platform, oil and gas platform. If you use an MMC here, you can see that if you have a failure in a device, okay, the nearest land mass may be hundreds of kilometers away. Okay, so getting a substitute is not so easy in some cases. Okay, when you are working in a remote place. Okay, and these are the pictures of the half bridge and full bridge cells, and this is the picture of a converter. Okay, and you can see how big is the size of the total converter. Okay, and this is the total size of the converter station. Okay, it's quite big, so you can understand the size of this by seeing the cars which are parked. At the top of the picture, you can see cars, some of the cars are parked. And from there, you can get an idea how big is this converter station. It may be the size of a football field or even more. So these are some of the design guidelines which we have covered. Okay, it's very rough design guideline, not the basic thing, because when you go to the industry, there are lots and lots of other features, temperature rise, which we have not covered. We have just given the voltage and current ratings, temperature rise, reliability, many analysis have to be done, okay, before you can actually design or choose a specific component. Okay, some of the case studies also we have done. And the case study with the cascaded edge bridge for motor drive application also we have covered here. Okay. Yeah, so I think this is what we will end here, okay, at this point of time. So I think we can close here. Okay, it's almost 1 hour now. Okay. So Sandeep ji, what should we do now?
Yes, sir, we can close, sir.
Okay, so is there any question?
No, sir, there is no any question, sir.
Achha, theek hai. So I will then close the session here, and I will also I'm always available by email. So if you have some questions, you can also post it in the forum, and that will be the first point of contact. But even after that, even when the course is over, then also you can contact me. Several students after the course have contacted me, and they send me emails whenever I have some time, and then I will answer them. And actually, many students, the feedback that I have got is that many students are getting benefited from the course, which is the main motto for which I am running the course. And so I wish you best of luck for the further exploration of this kind of high power converters in future.
Thank you, sir.